Okay, so welcome back to the afternoon session. We now have two single talks about the history of physics, and we would like to start with Ricardo Karam from the University of Copenhagen, and he will talk about the Schrödinger struggles with the complex wave function. So.
Yes, thank you so much. Good afternoon, everyone. First of all, thanks to the organizers for accepting this submission. By the time I saw the title History for Physics, I thought this is the conference I need to go because it's very nice to meet people and discuss about how important history is for physics. As you can see, I'm located at the Department of Science Education, so my main concern is with physics education and how can we use history in physics education with the training, including the training of future physicists. So of course, it is related to the physics as a research field as well. It is a pleasure and an honor to be in Vienna and talk about Schrödinger, so that was also quite a nice thing. Let me start by giving you a little bit of a background and motivation for that so that you can know what to expect and understand a little bit the kinds of things that motivated me to think about these things. I would say that my main motivation or what drives my research, what I'm constantly thinking about is the educational implications of the relationship between physics and mathematics. What makes it difficult for students? How can we improve teaching concerning this intrinsic mathematical aspect of physics? How challenging it is and everything. So what led me to history is really trying to understand better this relationship and how can we use original sources and everything to improve teaching. One episode, of course, talking about mathematics and physics is just too general to be productive at all, so we need to pick some episodes and to make sense of that particular, or the kind of relationship in a particular instance. I've been thinking for a while about the use of complex numbers, complex functions in physics. It's an interesting case because complex numbers emerged in mathematics. In Italy, they were not related to physics, and after a while, they become quite useful for physics. And it was a process that Salomon Bochner once called the complexification of physics. So it is within this context that you inevitably get to the question of, complex numbers, complex functions in quantum mechanics. And the common view is that, whereas complex numbers are quite useful calculation tools in classical physics, but they make calculations easier, but they are not necessarily indispensable or essential. The situation seems to be different in quantum mechanics. They are indispensable somehow. So that led to this kind of reasoning. Why exactly, and especially how can we then justify this to students? So now we get closer and closer to the question, but why is the wave function complex? And how important is that kind of question, for example, when a student is encountering this for the first time? David Kaiser mentioned that in Schiff's book, the Schrödinger equation appears in page 21, and I would say by far the most used textbook at universities nowadays in quantum mechanics, Griffiths, that is in page 1, right? So the time-dependent Schrödinger equation appears in page 1. You already might wonder, what is this I here doing? Here is a bit strange, a fundamental equation that's supposed to describe things in the real world, and there's an I there. In principle, it's already something strange. But, in page 2, you say, but that's not a problem, because when you talk about things that you can actually measure, its probability densities, you're talking about the absolute square of this, so it doesn't matter that it's complex, because, you get real numbers in the end, so that's not a problem. Let's move on. So there is an issue. I can completely understand the reasons why, let's give what is consensus and move on. So I'm not kind of saying that this doesn't do a purpose, but I'm just wondering from the point of view of a student, seeing that for the first time, never saw before something where these complex entities play such an essential role it might be something like, okay, how come, why, and everything. So the question was, okay, was that so natural to Schrödinger? I mean, how Schrödinger perceived this? So that was kind of what got me interested in this. And then it's fairly easy to find a struggle, so to speak, that Schrödinger, and he's quite explicit about that. And this is the topic I'm going to guide you through four instances of this process of initial struggles he had with the acceptance of a complex wave function. So, for example, he clearly states that in a letter to Lawrence in June 6, what is unpleasant here and indeed directly to be objected to is the use of complex numbers. Psi is fundamentally a real function. It's quite easy actually to find these kind of things in the beginning, especially letter 26 and yeah, especially 1926 we do find this. So here are the instances, the episodes that I want to present you and that show that some of Schrödinger's struggles with a complex psi. The first one is a classic and I would argue even usable for physics teaching when we get there. So in a very short communication, short paper called From Micro to Macro Mechanics, we can clearly see that he's after a physical interpretation only of the real part of his psi. And it's quite explicit, and we'll go to that in the first part of the talk. The second one is also interesting and easy. In the very beginning of his fourth communication, where it is for the first time he's presenting the time-dependent equation, he does something strange, which seems to somehow avoid the explicit appearance of this imaginary unit in the equation. There are deeper reasons for that. One could say, why isn't he writing the equation with this explicit I as we know today? These deep reasons are related to an idea that you might be able to find a unique relationship between the real and imaginary parts of the complex wave function, so that in a way it is also some kind of calculational tool, but the essence, the physical essence would be, for example, in the real part. We will go a little bit into that, and that was, I found a piece of a notebook where he's quite explicit about what he's doing. He does communicate the results to Lawrence in this letter, but here in the notebooks, he's like really going through a rather apparently basic step of separating the real and imaginary parts of the wave function and trying to get to some kind of relationship between them. And then in some sense, we find a year later indications where it somehow accepts and even justifies that the wave function needs to be complex. We'll go through in the last part. There's a series of lectures he gives in March 1928 called 4 Lectures on Quantum Mechanics. There he's very explicit, and he justifies both due to the need to preserve the Bohr frequency relation, and in an interesting way he says, he comes up with an analogy with Maxwell's equation. So this is, let's hope we go through this, that's the plan. So the first slide is this, is his interpretation of the real part. And this is a very short paper. He starts by presenting the solution of the harmonic oscillator. And then already, by the time he presents the solution, he already puts a footnote there. I means the square root of -1. On the right-hand side, the real part is to be taken as usual. Of course, we're dealing with waves. We write these complex exponentials, but this is just a very handy mathematical tool. Physical meaning is in the real part. So that's quite clear. And he even plots for several values of n the form of these functions here. And then he goes on and considers, what if we have a group of these many vibrations, and he will show how they can then come to represent this particle. So he writes psi as a sum of n to infinity, so he's adding all these proper functions. And he gets to this. There's some mathematical theorems that he gets from Hilbert and Courant always. And then he gets to this expression here, which there's still the I there. And then he again said, okay, but now we take as provided for the real part of the right-hand side. And then he gets to this expression. You see that there's no I here anymore because this is the real part of this expression here. And then he's commenting on what it happens with this function and this behavior and there and there. And then he makes this drawing here, which kind of looks like a compact wave packet. And he claims our wave group always remains compact and does not spread out into larger regions as time goes on, as we were accustomed to make it to do, for example, in optics. And then he ends the paper with a bold, but ends up to be a false prediction. We can definitely foresee that in a similar way, wave groups can be constructed, which move around highly quantized Kepler ellipses and are the representation by wave mechanics of the hydrogen electron. That turns out not to be the case. This is actually the only case where that happens, but it shows his wish, or how he was normally dealing with a wave formalism and how you would expect to represent a particle with this wave mechanics. I would just like to say this is 2 or 3 pages. We normally all teach the harmonic oscillator to first-year students or the first contact. I think it wouldn't be too demanding to just glance at this paper and have an idea of what Schrödinger was expecting from that. But that's a kind of an opinion or maybe a suggestion. When we look at the fourth communication where he presents his time-dependent equation, it does something apparently strange. So he starts from what he calls the amplitude equation or the time-independent equation, and then the goal is to eliminate this energy parameter, makes it more general, not depending on a particular energy parameter, and also involving how psi changes, varies with time. Then he assumes, okay, psi is there's some kind of frequency or periodicity in this function. And then from here, he actually derives it twice with respect to time. And then he gets this relationship, and in order to substitute this here and get rid of E, he somehow has to square this equation. And he gets to this rather complicated looking equation, and he's like, but then he's emphasizing this is the uniform general wave equation. So I would say Schrödinger in his fourth communication is claiming that this is the time-dependent Schrödinger equation. It is no longer of the simple type that we had before, but it is of the fourth order. I mean, you have second order in time, you have fourth order in space here. It is similar to some in elasticity and in vibrating plate. It's quite instructive to read the last paragraph of his fourth communication because he is not satisfied with the state of the theory, and he manifests that. He says, he ends the paper saying, meanwhile, there is no doubt a certain crudeness in the use of a complex wave function. If it were unavoidable in principle and not merely a facilitation of the calculation, this would mean that there are actually 2 wave functions, say the real and imaginary part, which must be used together in order to obtain information on the state of the system. This seems unacceptable. So he's not satisfied when you read the last paragraph. It's like, and then it was, he mentions, this part he does mention in the letter to Lawrence, but not the calculations. And then it was kind of it was by luck. I was glancing the notebooks. There's so many, and okay, you do have some references to which topics to look at, but I wasn't actually really expecting. I don't know how clear this can be here, but this page is quite interesting, where he's explicitly expressing his struggle and what is he trying to do here. And he would like to thank my colleague and friend Christian Jost to help me decipher this. But actually, in the beginning, one can read, was bedeutet überhaupt? What does it mean, psi times psi bar? And then it's something like, lässt sich das ohne Heranziehung des Komplexen physikalisch fassen? Can we interpret this without this complex structure, nature, physically? So that he writes there in the beginning. And then he does something, I'll try to go through this. So actually the continuation of that citation in the last part of the fourth communication is something like, that seems unacceptable, or it's not satisfied. The state should be given by a real function and its time derivative. And that's what he's trying to do here. I'll just give you an idea. It's actually quite simple. So he writes the psi as this expansion of proper functions, and then he considers that both C and, of course, this one, it has both a real and an imaginary part. This is what is written here. So he's separating the real and the imaginary part, and that enables him to explicitly write psi as some psi r plus I times psi I. So the real part plus an imaginary part, quite explicitly. It's just a bit difficult to see here because he's using kind of a capital psi for the real part and the normal lowercase psi for, so he's better, but he's talking about the real and the imaginary part. And then, well, he writes his equations just with a differential operator, and he gets to this relationship here, which is here. And we can see that his goal is somehow he's expressing the time derivative of psi as a function of the real part and the derivative of the real part. So that's kind of his initial goal. And in the end, he shows that, well, one gets this equation, at least for the conservative case, which essentially, so to speak, is just about the real part. So you can still have the physical interpretation there. Then when we look at 1 year later, after 26 and 27, for example, he writes a paper on the exchange of energy according to wave mechanics. You don't read that struggle or any kind of problem anymore. The first equation in the paper is this one, and he just adds a footnote. The wave function must be essentially complex. There's no, thanks. And then there are these 4 lectures on wave mechanics, which I think they are a pedagogical masterpiece. They are didactical. Really, I think it was an attempt to present his theory and his main ideas to some kind of general audience of students, for example, as if it were an undergraduate course or something. So in his 4 lectures, he goes back to the problem of removing the energy parameter from the amplitude equation, and he says this is easily done. Pretty much you derive psi with respect to time. Once you get your E, you substitute here, you get the equation there. So there's no problem with a complex wave function, or there's no discussion about what does the real part mean and the imaginary part mean. But then he still consciously, explicitly refers to this idea of why it has to be complex. So he's actually presenting some argument for that rather explicitly. This is still from the 4 lectures. He said, now return to the general vibration function, which is just the expansion of psi in proper functions. We put the question, is it possible to ascribe a definite physical meaning to the quantity psi in such a way that the emission of light with frequencies nu k, k prime is nu k minus nu k prime becomes intelligible? So here's the situation. Here's a concrete problem. He says, yes, it is, but strange to say, only if we make use of the complex psi function as it stands instead of its real part as we are accustomed to do in ordinary vibration problems. So here, he's a little bit more explicit, and he's saying, why is it that we actually need? So in a way, he says, well, if we want to preserve this relation, we need a complex function. And the hypothesis that he already presented before is the following. That's again from the 4 lectures. The square of the absolute value of psi is proportional to an electric density, which causes emission of light according to the laws of ordinary dynamics. So if you have psi times the conjugate of psi, you can kind of see, you get a term here, which is frequency term, which is exactly the difference between 2 frequencies. So in a way, you kind of have an idea, all right, if you want a frequency which is originated from the difference between 2 frequencies, this kind of mathematical structure gives you. And then the last is, which I also find quite interesting, he himself in the 4 lectures then argues, well, but if the physical meaning is on psi bar, why not replace the wave equation by an equation which describes the behavior of psi bar directly, right? This is what is physically meaningful, accessible. Why not do that? And then here's his reflection or comment. He refers to Maxwell's equations, and he says, Maxwell's equations describe the behavior of electromagnetic vectors. But these are not really accessible to observation. The only things that are observable are the ponderomotive forces, or if you please, the energy, since the forces are caused by virtual energy. But all these quantities, energy, Maxwellian stresses, they are quadratic functions of the field vectors. Therefore, we might desire to replace Maxwell's equations by others that determine the observable quadratic functions of the field vectors directly. But everyone will agree that this would, at all events, mean an immense complication, and that it would not really be possible to do without Maxwell's equations. So, in a way, he's saying this is formally similar to what Maxwell's equations do. You have the quadratic functions, which are the ones that you observe, but you wouldn't wish to have these equations. Everyone would agree that Maxwell's equations is better, so it's pretty okay to have the equations initially in the complex form. So this is kind of an outline of a sketch of a process of initial struggle, because formally he was not only committed to this wave picture of the world, but naturally to the formalism, and that's how wave formalism used to think and use complex numbers with. But somehow the process, in 1 year, is a little bit accepting and justifying the use or the need for this complex wave function. That was it. Thanks for your attention.
So thank you very much for the interesting talk. We now have 5 minutes for questions. So
I enjoyed this very much.
Thanks, Chris.
It reminded me that Bohr was also rather skeptical about the introduction of I. And I remember a passage somewhere, I could dig it up. I don't have it at the top of my head, but I could dig it up for you, where in some later paper, Bohr laments the necessary introduction of the symbolic. He would use phrases like this, the symbolic procedure of introducing the imaginary number for the purpose of simplifying the equations. So he seems to similarly have the same mindset that one could write the equations of quantum mechanics without the I, but then they would be very complex and ugly. And it was only the introduction of the I that allowed one to see the simplicity of just going straight from Hamilton's equations down to Heisenberg dynamics, I think. So there must have been an immense struggle in many people. This must have been a kind of cognitive dissonance, not only for Schrödinger, but there's also evidence of Bohr and then maybe everyone else. Why this I?
Thanks. I'll be very interested in looking at that. I've been looking at how they would, for example, express a Fourier expansion of something. Just, how do you write the expansion? And, for example, I saw that when Bohr writes, and he's talking, I think it's 1918 or something, in the correspondence principle of some of them, he writes as an expansion of cosines. And when Heisenberg comes in, also in his work, previous work in optics with commas and everything, it's clearly already with the complex exponential. So it's interesting at that time to see, okay, this is it just a different mathematical convenience, or when is it that it's physically essential somehow? I would love, if you know, if you dig it, I would love to look at that. Thanks.
Okay, are there any other questions? Oh, yeah.
Thank you very much. I'm interested in the paper where you read the quote that you put on the acceptance slide. Where did you say that? This is not a paper. This is a series of lectures. Those are 4 lectures on wave mechanics. It's very easily to find online. So it's called, it's really much called like this, 4 lectures on wave mechanics. Schrödinger gave in March 1928 in London. And to me, it's a didactical masterpiece, at least at the time. It's a very well-structured presentation of his ideas and thoughts. Okay, thanks. Hi, Ricardo. Thank you very much for the lecture. As a pedagogical strategy, I think it's very fascinating. But what is the expected reaction of the grad students to this kind of pedagogical strategies? Did you go any further in this evaluation?
No, not yet. Thank you. It's this what I mentioned is really like, I don't know, a guess or an invitation. You know, I think it's fair to say that this first wondering about why do I have now this complex thing that would kind of be a natural, wondering at least. And so I would think that at least ideally it would be nice to think about how can we actually give some reasons why and already for the introductory level. I haven't tried it yet, and I know that there is a dangerous balance there, of course, right? So in this sense, I would fully agree with what David Kaiser said. Sometimes it can be, okay, this is too distractive now. It's really like, it's going. So that's why I think this paper, this short episode, is the kind of thing that I think it adds without being too distractive. And those are often difficult to find, actually.
Okay, we have one short remark, then we have to move on.
It's indeed a remark. Yeah. Thanks very much for was very inspiring talk for this approach to didactics. Now, I just wanted to point out that the Schrödinger's papers are above our heads. Four floors above you find the collection of Schrödinger's paper here, and most of them have been digitalized and are accessible through the servers of our library. So for people who are doing research on Schrödinger, this is a resource that has been recently acquired by the University of Vienna, and they are accessible now.
Nice.
So let's thank the speaker again. Thank you very much.